Far beyond the Milky Way, the universe is not evenly filled. In the largest maps ever made, astronomers notice a region where the usual pattern of galaxies thins out, as if a wide piece of the cosmic web goes quiet. The shape is not a hole in space, but a vast underdensity, a basin where matter and light are both harder to find, outlined by brighter walls of galaxies at its edge. Over the next moments, the story follows the evidence from the wider surveys down into what the gap may contain: faint galaxies, thin intergalactic gas, and the hidden pull of dark matter that still shapes it. If this calm, science-based journey helps with sleep, focus, or slow learning, a like and a subscription support the channel and keep these long, quiet documentaries coming. At the largest reach of observation, the universe appears as a deep field of faint light, spread across black space and broken into countless points and hazy smudges. Each point is a source whose light travels through expanding space for an immense span of time before it enters a telescope mirror and becomes a measurable signal. The farthest sources are not simply far away in distance, they are also far back in time, because light has a finite speed. Astronomers describe this reach as the observable universe, meaning the portion of the whole cosmos that can, in principle, send light to Earth since the beginning of cosmic history. Beyond that reach, there may be more space and more matter, but no signal from there has had enough time to arrive. The size of this observable realm depends on how distance is defined in an expanding universe. Light that has travelled for about 13.8 billion years does not mean the farthest visible matter is only 13.8 billion light-years away today. While the light is in flight, space continues to expand, increasing the present-day separation between the source region and Earth. Using the standard cosmological model, astronomers estimate that the present-day radius of the observable universe is about 46 billion light-years. This number is not an edge drawn on space like a border on a map. It comes from the history of expansion and the paths light can take through space-time to reach an observer. This boundary is not a hard wall. It is a limit set by time, by expansion, and by the changing state of the early cosmos. When astronomers look to great distances, they look along a path through cosmic history. Nearby, galaxies appear large and structured, with bright star-forming regions, dark dust lanes, and faint halos of older stars. Farther out, galaxies shrink into small patches of light, and details blend into simpler shapes. Farther still, galaxies become difficult to detect, not because the universe ends, but because the earliest galaxies are small, and their light is stretched by expansion into longer wavelengths. Space itself grows, and this growth stretches each wave of light, so that what begins as energetic ultraviolet light can arrive as infrared light. Telescopes sensitive to infrared light therefore extend the view into earlier times. The observable reach is also limited by a shift in physical conditions. In the first hundreds of thousands of years after the beginning, matter is hot, dense, and filled with charged particles. Light in that era does not travel freely. Photons scatter again and again from free electrons, and the cosmos behaves like a bright fog. As expansion continues, the temperature falls. Electrons join with nuclei to form neutral atoms, and light begins to stream through space with far fewer collisions. The afterglow of that transition remains visible today as the cosmic microwave background, a nearly uniform field of microwave light coming from all directions. It records a time, not a place, and it marks the earliest moment the cosmos becomes transparent to light. This ancient background sets a practical edge to direct vision. because earlier times are hidden behind the opaque plasma that comes before. Its light has been travelling for about 13.8 billion years, and it has cooled as the universe expands, shifting from shorter wavelengths to microwaves. Tiny variations across the sky reveal that the early cosmos is not perfectly smooth. These differences are small at first, yet they matter. Over billions of years, gravity amplifies them, drawing matter into denser regions and leaving other regions more empty. Cosmology treats space and time as a connected structure, so distance is not fixed in the way it is in everyday experience. Two galaxies that are not bound by gravity tend to separate as space expands between them. Astronomers infer this expansion by measuring redshift, the stretching of light to longer wavelengths. A galaxy with a higher redshift is generally observed as it was earlier in cosmic time, and it is also associated with a greater distance in the expanding geometry. Converting redshift into a distance involves a model of how expansion changes through time, constrained by measurements of background light, galaxy distributions, and well-studied cosmic explosions. Dark energy is the name given to the observed tendency for expansion to accelerate over the last several billion years. Its nature remains uncertain, but its influence on distance estimates is handled within the standard cosmological model used to map large volumes of space. This model also includes ordinary matter, dark matter, and a small contribution from radiation. In this framework, the observable universe is not only a region of space, but also a record of evolving conditions, since every distance measurement is tied to a time in the past. Within the observable volume, matter is not uniform in detail. On the larger scales, the cosmos is close to the same in every direction when averaged over vast distances, an idea called cosmic homogeneity and isotropy. This is a statistical statement, not a claim that matter is evenly spread. When astronomers average over regions hundreds of millions of light-years across, the overall density approaches a common value. At smaller scales, matter clumps strongly. Galaxies gather into groups, groups into clusters, and clusters into larger associations. Between these structures lie immense regions with fewer galaxies and less matter. In everyday language, these can be called gaps, but in cosmology, they are described with careful measures of density, size, and shape. A region can be relatively empty compared with the cosmic average and still contain diffuse gas, dark matter, and a sparse population of faint galaxies. A region can also appear empty because the light from distant galaxies is blocked or scattered by dust in the Milky Way, or because a survey does not cover a patch of sky with equal sensitivity. For that reason, astronomers separate the cosmic boundary from the limits of human observation. The cosmic boundary is set by physics and time. The observational boundary is set by detectors, wavelength choices, and the correction of biases. When scientists report an unusual gap, they begin by placing it within this widest context of what can be observed at all, what can be measured reliably, and what remains hidden by the limits of light and expansion. Across the observable universe, matter arranges itself in a pattern that is neither random scatter nor smooth fog. On very large scales, the average density approaches a common value. Yet within that average, the contents of space gather into a connected architecture. Astronomers call this architecture the cosmic web, meaning the vast network formed as gravity draws matter together over billions of years. The term refers to the arrangement of matter on scales far larger than any single galaxy, where gravity acts across immense volumes and long time. In this web, galaxies tend to lie along elongated bridges, converge in crowded hubs, and thin out across broad surfaces that curve through space. The map is not made of continuous lines but of many separate systems whose positions reveal an underlying shape. The richest knots of the web are clusters of galaxies. A cluster is a gravitationally bound assembly containing hundreds to thousands of galaxies, immersed in hot gas and dominated by dark matter. Clusters sit where multiple strands meet. Around them lie smaller associations called groups, where a few to a few dozen galaxies share a common dark matter halo. Between groups and clusters, the web stretches outward into filaments, long regions where matter density is higher than average but far lower than in clusters. Filaments can extend for hundreds of millions of light years, narrowing into delicate bridges between heavier hubs. The web also includes broad, sheet-like regions, sometimes described as walls. These are flattened concentrations formed when gravity compresses matter more strongly along one direction than the others. In a slice through space, a wall can appear as an extended band of galaxies, with strands feeding into it and less populated regions on either side. In 3 dimensions, such surfaces fold and merge, creating a layered landscape rather than a simple grid. The cosmic web is a measurable outcome of known physics. It begins with tiny differences in density in the early universe, recorded as slight variations in the cosmic microwave background. Where density is a little higher, gravity pulls in more matter. As material flows inward, the dense region becomes denser, and surrounding regions lose some of their contents. Over time, this feedback produces a landscape of peaks and basins in density. The peaks evolve into clusters, groups, and the strands that connect them. The basins become very low-density regions. The web is the mature form of this growth, shaped by the interplay between gravitational attraction and the general expansion of space. Dark matter plays the central role in building the web. It interacts mainly through gravity and does not emit light, so its distribution is inferred rather than seen directly. In the standard picture, dark matter clumps early, forming halos that grow by merging and by drawing in nearby material. Ordinary matter follows the dark matter's pull, but it behaves differently because it can collide, heat, cool, and form stars. Gas falls into dark matter concentrations, warms as it compresses, and in many places cools enough to collapse further and form galaxies. The visible galaxies therefore trace the densest ridges of a much larger, mostly invisible framework. The match is close but not perfect, because galaxy formation depends on local conditions and on energetic processes that can drive gas outward. Several kinds of evidence support this picture. The motions of galaxies and clusters reveal much more mass than can be accounted for by stars alone. Hot gas in clusters shines in X-ray light, and its temperature indicates a deep gravitational well. Gravitational lensing, the bending of light by mass, shows that most cluster mass lies in extended halos beyond the visible galaxies. On larger scales, the way galaxies cluster together across space also points to a dominant, unseen component shaping the pattern. Astronomers describe clustering as the tendency for galaxies to be found near other galaxies more often than chance would predict, and this tendency changes with scale. When measured across vast surveys, the clustering pattern contains a faint imprint from early cosmic sound waves called baryon acoustic oscillation, a subtle preference for galaxy pairs to be separated by about 500 million light-years. To see the web, astronomers must go beyond a flat view of the sky. A 2-dimensional map mixes near and far objects together, hiding depth. When distance information is added, the distribution becomes a 3-dimensional atlas. Distance in cosmology is estimated from redshift, the stretching of light to longer wavelengths as space expands, and from other calibrated indicators. With enough measurements, a survey can place millions of galaxies into a volume map. Within that map, filaments appear as elongated concentrations and clusters appear as dense nodes. The web emerges more clearly when the map is sliced into thin layers of distance, because structures that are distinct in depth can overlap in projection. Some regions contain rich intersections with many thick strands, while others contain fewer hubs and thinner bridges. This variety is expected because the initial density differences are random in their exact arrangement. Computer simulations provide another perspective. When a model begins with early density variations consistent with the cosmic microwave background and then follows gravity forward through time, a web of filaments and clusters forms naturally. When ordinary matter is included with simplified rules for gas behavior and star formation, luminous galaxies appear preferentially along the same dense ridges. The broad agreement between simulated patterns and observed surveys is one reason the cosmic web is treated as a robust feature of the standard cosmological model. The scale of the web is vast compared with individual galaxies. A typical galaxy spans tens of thousands of light years, while the strands that shape galaxy placement can run for hundreds of millions of light years. Even so, the web is delicate because the average density across these distances is extremely low by everyday standards. Structure is defined by relative differences rather than by crowded material filling space. Within this connected architecture, regions of high density and regions of low density belong to the same continuous geometry, both shaped by gravity acting over long time and by the steady expansion of space. Within the cosmic web, the broadest quiet spaces are the voids, immense regions where galaxies become scarce, and the inferred matter density falls below the cosmic average. A void is not a hole cut out of space. It is a volume shaped by the same gravity and expansion that shape clusters and filaments, but it evolves in the opposite direction, becoming emptier as matter drifts away. In wide maps, voids appear as pale interiors surrounded by brighter rims, where filaments and walls trace the boundaries like coastlines. The edges are not sharp surfaces, they are gradual transitions, where density rises from low values in the interior to higher values in the surrounding web. A void can be roughly round, stretched, or irregular, depending on the nearby structures that confine it. Void sizes vary. Some span a few tens of millions of light years, nested among neighboring filaments. Others reach more than 100 million light years across, broad enough that their interiors hold only a sparse scattering of faint galaxies. Even the largest void is not empty. Dark matter remains present, though in smaller amounts than average, and diffuse gas fills the volume at extremely low density. When density is measured relative to the cosmic mean, many well-studied void interiors fall well below that mean, sometimes containing only a small fraction of the average matter in the same volume. Yet because the universe is so large, even a low-density region holds substantial mass in total. A small population of galaxies can exist inside, often smaller and more isolated than the galaxies that crowd the surrounding walls. The interior environment matters because isolation changes how often galaxies interact and merge, and it changes how easily they draw in new material from their surroundings. Many voids contain a delicate internal network of faint filaments, too thin to rival the walls outside, but still showing that structure does not vanish entirely. A void is defined by how matter is traced. In a galaxy map, it is a region where galaxies are uncommon compared with the survey's mean density. In a mass map inferred from gravitational effects, it is a region where total mass density is low. These definitions are closely related, yet they are not identical. because galaxies form preferentially in denser dark matter halos. Light therefore highlights ridges more strongly than the underlying mass field does. A void outlined by galaxies can look deeper or larger than the true dip in total mass. Astronomers handle this by comparing different traces and by using simulations that connect visible galaxies to the dark matter framework. The boundaries of voids are active in a quiet way. Gravity pulls matter toward denser regions, and this pull produces a flow that tends to move mass out of void interiors and into surrounding filaments and clusters. Over time, the interior density falls further below average, while the rim becomes more pronounced as material gathers. In the expanding universe, the general stretching of space carries everything outward, yet local gravity still organizes motion into patterns of convergence and divergence. In dense nodes, flow converges inward. In void interiors, flow diverges outward, creating a gentle drift toward the edge. The result is a large-scale motion field in which voids behave like sources of outflow and clusters behave like sinks of inflow, with filaments guiding material between them. Voids also evolve through merging. Nearby underdense regions can expand until their boundaries meet, and the thin wall between them weakens and dissolves. Smaller voids combine into larger ones, producing a hierarchy of emptiness. This nesting reflects the early density field, which contains fluctuations on many scales. Where the early universe is slightly underdense on both a small scale and a larger scale, a smaller void grows within a broader basin. Where a small underdense patch lies inside a larger overdense region, its growth can be limited by the surrounding pull, leaving a shallower, more compressed void. Both situations occur in the standard model, and they help explain why voids differ in shape and depth. The origin of a void begins when density differences are tiny but real. A slightly underdense region contains less mass than average in the same volume. Gravity within that region is weaker than in its surroundings, because there is less mass to pull inward. As the universe expands, the underdense region expands a little faster than average, because there is less gravitational deceleration. Over cosmic time, this difference accumulates. Matter drifts away from the underdense center, and the region becomes emptier. The surrounding slightly denser regions slow their expansion more and begin to draw in matter. Contrast grows steadily. In this way, voids and clusters are two sides of the same process, both seeded by early variations and both shaped by the long balance between expansion and gravity. As a void grows, its interior becomes smoother in a particular sense. Small clumps inside are stretched and diluted, and the lowest densities tend to settle toward the center. The most prominent remaining structures lie closer to the boundary, where matter that leaves the interior accumulates. This produces a characteristic density profile, with the deepest underdensity near the center and a rise toward the rim. In some cases, the rim becomes denser than the cosmic average in a shell-like zone where material piles up. The exact profile depends on environment and on the void's history of merging, but the general pattern of a low interior and a denser boundary is common. Voids therefore carry information about how structure grows. Their sizes, shapes, and abundance reflect the statistics of the early density field and the way gravity amplifies it. They also depend on the overall matter content of the universe and on how the expansion rate changes through time. Observations indicate that voids are common and that a large fraction of cosmic volume lies in low-density regions rather than in the crowded hubs. It remains uncertain in fine detail how best to draw a boundary around a continuous field, and different methods can define slightly different edges. Yet the existence of vast underdense regions is not in doubt. The cosmic web is built not only from bright concentrations, but also from the immense spaces between them, shaped into voids that expand, merge, and persist across billions of years. A void becomes notable when it's not only large and quiet, but also discordant with the surrounding pattern beyond what astronomers expect from ordinary variation. In survey language, an underdense region becomes a reported gap when maps show an extended stretch of space where the usual traces of matter thin out more than anticipated, or where the thinning persists across a scale that seems unusually broad. The word gap evokes absence, yet scientific judgment rests on measured density contrasts, defined volumes, and comparisons with what a survey should reveal in that part of the sky. In a typical cosmic map, many voids appear, and most of them blend into a continuous range of sizes and depths. A region begins to stand apart when the emptiness appears too deep, too wide, or too coherent compared with the surrounding web, especially when it is identified repeatedly by different mapping methods. The claim is not that space is missing, but that the matter distribution contains an unusually low-density basin. Some studies call such a feature a supervoid, meaning a void near the largest end of the expected spectrum. Other studies describe an extended underdensity along a line of sight, meaning that galaxy counts remain low across a long range of distances in the same direction. To describe such a feature, astronomers first choose a tracer. Often, the tracer is a catalogue of galaxies within a survey, each with a sky position and a distance estimate. From this catalogue, they estimate a density field by counting galaxies in windows, smoothing the distribution, or applying an algorithm that identifies basins in the density landscape. They then define a centre, an effective size, and an average depth. Depth is measured as the fractional difference between the local tracer density and the survey mean, after accounting for how the survey's sensitivity changes with distance. A deep region means that the tracer density inside the chosen volume is far below average. The definition depends on scale. If the density field is smoothed over a small region, the map highlights smaller basins and breaks large, low-density zones into many parts. If smoothing is coarse, smaller features blur away and the map emphasizes only the broadest depressions. In a sparse catalogue, random counting fluctuations can also create apparent holes, a problem known as shot noise, and the risk grows when a survey samples only the brightest galaxies. For this reason, a reported gap carries with it a record of choices about smoothing length, sampling, and the algorithm used to draw boundaries through a continuous field. The case for an unusual gap strengthens when the feature persists across overlapping surveys with different instruments and selection methods. Surveys often include masks, regions removed because bright stars, detector artifacts, or dust obscure background galaxies. If an underdensity follows the edge of a mask or sits where observations are shallow, the feature may reflect the survey rather than the cosmos. If instead it appears in independent datasets and in more than one tracer population, such as galaxies selected by different wavelengths or brightness ranges, then the likelihood of a genuine cosmic underdensity increases. The judgment of unusualness is statistical. The standard cosmological model predicts a distribution of void sizes and depths in a universe, with the measured matter content and the measured pattern of early fluctuations. Large simulations and analytic models allow astronomers to estimate how often a void of a given size and depth should occur in a survey volume. An outlier can be rare without being inconsistent, because a large survey contains many opportunities for extremes. The number of independent regions searched matters, and the most extreme structure in a vast map is expected to look more extreme than the typical one simply because many volumes are tested. A separate complication comes from how a gap is selected. Sometimes the first hint comes from a visual impression in a map, or from attention drawn by a feature in another dataset. Once focus falls on a particular direction, analysis choices that define the boundary, depth, or center can shift the measured strength of the underdensity. This does not imply error, but it makes probability estimates less clean, because the region is partly chosen after inspection. Careful studies test alternative definitions and ask whether the underdensity remains robust under reasonable changes in method. Distance uncertainty also reshapes a gap. Most large surveys infer distance from redshift. Redshift is affected mainly by cosmic expansion, but it is also affected by local motions as galaxies fall toward dense regions or flow away from underdense ones. These motions blur boundaries along the line of sight and can make a region look stretched or compressed in redshift space. Survey completeness changes with distance as faint galaxies drop below detection limits, and corrections for this effect carry uncertainty. Small mismatches in correction can make a normal underdensity appear deeper, or can partially fill a genuine underdensity. The depth inferred from galaxies also depends on how galaxies populate dark matter halos. In low-density environments, the total mass field can be only moderately underdense, while the visible galaxy count drops more sharply, because fewer halos reach the masses that host luminous galaxies. Observations indicate that galaxy voids generally correspond to true underdensities in mass, yet the exact depth in dark matter can differ from the depth in galaxies, especially when only one tracer population is used. It remains uncertain in many cases whether an apparent extreme in galaxy counts implies an equally extreme deficit in total mass. A claimed mysterious gap therefore sits at the intersection of measurement and expectation. It is mysterious only in the sense that it lies near the edge of what is common in a given survey, and it motivates checks for bias, completeness, and consistency across methods. Some reported gaps soften when additional data fill in distances or when the surveyed sky area widens. Others persist as broad, coherent underdensities that remain compatible with the far tail of standard predictions. In either case, the scientific work rests on defining the region precisely and comparing it to the full range of structures expected in a universe where emptiness and concentration arise together, guided by gravity over billions of years. Once a suspected gap is identified in the broad pattern of galaxy distribution, the next layer of work focuses on the practical path from faint light to a three-dimensional map. The raw material is a sky filled with points of differing brightness and colour, each one recorded by a camera or spectrograph as a pattern of photons arriving over time. A survey begins by choosing where to look, how deep to look, and which wavelengths to record. It then turns these choices into catalogues, lists of objects with measured positions, brightness, and other properties. From these catalogues, distance estimates are derived, and only then does the idea of a void or gap become measurable as a volume. The first mapping step is identification. A survey image contains stars from the Milky Way, distant galaxies, and occasional artifacts. Algorithms classify objects based on shape and brightness profile. Stars tend to be point-like, while galaxies have extended profiles, though very distant galaxies can appear nearly point-like as well. Color information helps separate populations because stars and galaxies have different spectral shapes. These classifications are not perfect, especially near the survey's detection limit, and errors can produce false changes in galaxy density. A good map therefore includes careful estimates of completeness, the fraction of real galaxies detected as a function of brightness, color, and position on the sky. The second step is distance estimation. For the largest surveys, the most direct approach uses redshift. Redshift is measured by comparing an object's spectrum to known patterns, where absorption or emission features shift to longer wavelengths in proportion to cosmic expansion. Spectroscopic redshifts are precise, but spectra take time to collect, so they are often available for a subset of galaxies. Many surveys use photometric redshifts, which estimate redshift from brightness measured in several color bands. This approach allows many more objects to be mapped, but it carries larger uncertainty. The uncertainty tends to grow at faint magnitudes and at higher redshift, where key spectral features move between filters. When a gap is mapped with photometric distances, its boundaries blur, and the measured depth can be diluted if galaxies are scattered into and out of the region by distance errors. A third step converts redshift into a comoving coordinate system. In an expanding universe, comoving distance is a way of labeling positions so that the overall expansion is factored out, letting astronomers compare structures at different times as if using a grid that stretches with space. This conversion depends on the expansion history, which is set by the cosmological model parameters. For most large-scale structure studies, the uncertainties in these parameters produce small changes compared with survey measurement errors, but they are still accounted for in careful analysis. The resulting map places each galaxy at a position in 3 dimensions, with 2 angles on the sky and 1 distance along the line of sight. With a 3-dimensional catalogue, density estimation begins. Because galaxies are discrete objects, the density field is built by counting and smoothing. One approach divides the volume into cells and counts galaxies in each cell, then smooths the counts over neighbouring cells to reduce noise. Another approach uses adaptive methods that change smoothing scale depending on local density, preserving sharp features in dense regions and reducing noise in sparse ones. Some algorithms identify voids by finding local minima in the density field and then growing a region outward until a boundary criterion is met, often where density rises above a threshold. Other algorithms use geometric constructions, such as assigning each galaxy a region of space closer to it than to any other galaxy, and then identifying basins in this partition. Each method has strengths and weaknesses, and the choice affects how a gap is described. The survey itself imprints patterns that must be corrected. The most obvious imprint is the footprint, the portion of the sky observed. The footprint can contain holes where bright stars saturate detectors or where imaging conditions are poor. It can have varying depth, meaning different limiting brightness in different areas. A shallow patch detects fewer distant galaxies, mimicking an underdensity along the line of sight. To correct for this, surveys build completeness maps that record how detection probability varies with sky position, observing conditions, and brightness. These maps are used to weight counts or to exclude regions where completeness is too low. When a claimed gap lies near a boundary between deep and shallow observations, extra caution is required. Another imprint comes from the Milky Way itself. Dust in the galactic disk absorbs and scatters light, dimming background galaxies and shifting their colors. If extinction correction is imperfect, galaxy counts can drop in dusty regions, creating false low-density patches. Surveys therefore use independent dust maps to correct for extinction and often avoid regions near the galactic plane. Even at higher galactic latitudes, small dust variations can matter for faint galaxy counts. A robust gap should persist after such corrections and should not align with known dust structures. Beyond these observational effects, there is a physical imprint from redshift space distortions. Galaxies are not carried only by expansion, they also have local motions. In dense clusters, Random motions stretch the cluster along the line of sight in redshift space, creating elongated features sometimes called fingers. In and around voids, coherent outflow motions can compress or stretch the apparent shape depending on direction and on the mapping method. These effects are predicted by the standard model and can even be used as a test of gravity on large scales, but they complicate the translation from observed redshift to real space structure. Analyses that focus on the existence of a gap often model these distortions to estimate the true density field more accurately. To judge whether a gap is real and how deep it is, astronomers often create mock catalogues. These are synthetic surveys drawn from simulations that include the cosmic web and the survey's selection effects. The mock catalogues replicate the footprint, completeness, distance errors, and tracer properties. When the same void-finding method is applied to mocks, the distribution of void properties in a realistic survey environment can be measured. If the observed gap falls within the range produced by mocks, it is consistent with expectations. If it lies well beyond, the gap becomes more noteworthy, though the conclusion still depends on how faithfully the mocks capture the real survey. In this stage, the gap is no longer an impression of emptiness. It becomes a set of measured properties, each one tied to the chain of steps from photon counts to redshift estimates to density reconstruction. The uncertainties are not hidden. They are part of the map, shaping how strongly the underdensity can be stated and how confidently it can be separated from the limitations of observation. After the map-making steps are tested and corrected, attention settles on the boundary of the reported gap, the region where the underdensity meets the surrounding web. This boundary is often where the evidence is clearest because it contains the structures that are easiest to detect. In surveys, the edge can appear as a ring or shell-like increase in galaxy counts, a wall of systems that outlines the emptier interior. The boundary is not a single surface. It is a thick zone where density rises, where filaments converge, and where the character of galaxies shifts in subtle but measurable ways. Galaxies are not all the same. They vary in mass, shape, gas content, and the rate at which they form new stars. A useful broad distinction separates galaxies that are actively forming stars from those that are more quiescent, meaning they form stars slowly and contain less cold gas. Star-forming galaxies often appear bluer because young. Hot stars emit more short-wavelength light. Quiescent galaxies often appear redder because their light is dominated by older stars. This color difference is not a rule without exceptions, but it correlates with environment. Dense regions such as clusters tend to host more quiescent galaxies, while lower density regions host a larger fraction of star-forming ones. The boundary of a void or gap, where density is moderate and interactions with the surrounding web occur, provides a place to study how environment influences these traits. Near the edges, galaxies are more likely to lie in filaments and groups than in rich clusters, and the local density can vary strongly over short distances. A filament is not simply a line on a map. It is a physical region where dark matter density is elevated and where gas flows along preferred paths toward deeper gravitational wells. Galaxies in filaments can experience a steady supply of gas from the surrounding medium, feeding star formation, yet they can also experience gentle gravitational interactions as they pass near neighbors. The boundary zone can therefore contain galaxies that are moderately active, with properties intermediate between isolated field galaxies and cluster members. When a large gap is present, the boundary can be extensive and can include multiple filaments and walls at different distances. Some parts of the rim may be dominated by a massive structure, such as a supercluster, while other parts may be made of thinner, more dispersed filaments. This variety matters because a gap is often defined by the absence of galaxies in the interior, but its shape and stability are controlled by the mass distribution around it. Where the surrounding structures are strong, they can draw matter more efficiently, deepening the underdensity. Where surrounding structures are weaker, the gap may be shallower and may merge more readily with adjacent underdense regions. Observations of the boundary often use more than simple counts. Galaxy clustering statistics can measure how sharply density rises at the rim. One approach measures the radial density profile around the void center, averaging over angles to find the typical rise. Another approach studies the distribution of galaxy pairs, revealing how the boundary contributes to correlations at specific scales. Such measurements are compared with simulations to infer whether the observed edge corresponds to a deep mass underdensity, or mainly to a deficit in the chosen galaxy population. Spectroscopic information, when available, adds further detail. Emission lines in galaxy spectra indicate active star formation and the presence of ionized gas. Absorption features can indicate older stellar populations. By sampling galaxies near the rim, astronomers can test whether the boundary environment shifts the balance of star-forming and quiescent systems. The expected trend is that the interior of a void contains more isolated star-forming dwarf galaxies, while the rim contains a mix including more massive systems and more groups. Yet the exact balance depends on the gap's depth and on the surrounding large-scale structures, and there can be significant scatter. The boundary also influences how distances are interpreted in redshift surveys. Because galaxies at the rim participate in coherent flows, their redshifts include contributions from local motion. In the vicinity of an underdensity, galaxies tend to stream outward from the interior toward denser surroundings. This outflow produces a systematic shift in observed redshift, relative to what would be expected from expansion alone. When a void is stacked across many examples, this effect produces a characteristic distortion pattern that can be modeled to test gravity. For a single prominent gap, the distortion can change the apparent thickness and symmetry of the boundary. Correcting for this requires models of the velocity field informed by simulations and by the observed distribution of matter around the region. The rim can also be examined through gravitational lensing. Lensing measures the integrated mass along the line of sight by the way it subtly distorts the shapes of background galaxies. A void or gap produces a weak lensing signal with the opposite sign to that of a cluster, instead of producing a net tangential stretching associated with a mass concentration. A deep underdensity can produce a slight radial pattern, reflecting less mass than average. The signal is faint and usually requires stacking many voids to detect robustly. For an unusually large gap, targeted studies may look for a lensing imprint from the region, but the uncertainty remains large because lensing integrates all matter along the line of sight, mixing the gap with unrelated structures in front and behind. As attention remains on the boundary, the gap becomes a region defined not only by what is missing, but by what surrounds it. The rim carries the clearest signs of the cosmic web groups and filaments that outline the underdensity and reveal the direction of matter flows. It is here that the gap is most tightly connected to the rest of the universe's structure, and here that observational tests can separate a simple shortage of luminous traces from a true deficit in underlying mass. Inside the reported gap, the map grows quieter in a way that is measurable rather than absolute. The interior is defined by a low number of luminous galaxies compared with the cosmic average for the same volume. In practice, when the region is divided into comparable chunks of space, fewer galaxies appear in the chunks that fall within the gap. The emptiness is never total. What changes is the spacing between the systems that wide surveys most easily detect. In a deep underdensity, the separation between bright galaxies increases, and the interior begins to resemble a wide ocean with only a few islands of light. A central reason for this sparsity is that the underlying mass field is reduced. In the standard picture of structure growth, galaxies form inside dark matter halos, and the abundance of halos depends on the local density environment. A dense region contains many halos, including rare high-mass ones. A void interior contains fewer halos overall and a strong deficit of massive halos. The gap therefore contains fewer large galaxies and fewer rich groups. When galaxies do appear, they often sit in smaller halos and contain fewer stars, making them faint and sometimes compact. Many lie near the detection limits of surveys, especially at great distances where light is dim and stretched. The apparent depth of a gap can therefore depend on how deeply the observations reach into the faint end of the galaxy population. Even in a genuine underdensity, the interior is not perfectly smooth. Thin internal ridges can remain, delicate structures that persist on smaller scales within the broader basin. These inner strands are low in density compared with the outer walls, yet they can guide where the few galaxies appear. A map sensitive only to bright galaxies can miss these strands and show an almost empty volume, while a deeper map can reveal a sparse network of small galaxies tracing weak connective paths. This difference reflects the way visible tracers emphasize only the densest parts of an underlying mass landscape. The meaning of low density becomes clearer when translated into physical terms. On human scales, emptiness suggests vacuum. On cosmic scales, even an underdense region contains material, but that material is spread so thinly that it rarely collides or shines. The average density of the universe is already extremely low by terrestrial standards, and a deep gap represents a further reduction relative to that rarefied mean. Gravity remains present, but its net pull is weaker, because there is less mass nearby to create steep gradients. The result is not stillness. Over long time, matter and galaxies drift outward from the interior toward the denser rim, a motion that unfolds over billions of years and slowly increases the contrast between center and boundary. Because the environment is gentle, close encounters between galaxies inside the gap are uncommon. Mergers occur less often because neighbors are rarer, and typical separations are larger. Tidal interactions, where galaxies pass near enough to distort one another, are also reduced. This relative isolation can preserve fragile structures in small galaxies and can allow their evolution to proceed without frequent external disturbance. Isolation, however, does not guarantee steady growth. A galaxy's ability to form stars depends on its internal gas, on heating and cooling in its surrounding halo, and on feedback from its own stars that can push material outward. The small galaxies found in underdense interiors often show traits linked to low mass. Their gravitational wells are shallow, so energetic events connected to star formation can more easily drive gas away, limiting how many stars form over time. Heavy elements are made in stars and dispersed by winds and explosions, and small systems can lose a larger fraction of this enriched material, leaving them with lower typical metal content than similar galaxies in denser environments. The overall trend is gradual rather than dramatic, and individual histories vary, but the interior favors systems that grow slowly, with fewer mergers and fewer episodes of rapid build-up. The interior is also shaped by the region's history. A large underdensity grows from an early basin in the primordial density field. As matter flows away from the center, the remaining structures become more widely separated. If the gap results from the merging of smaller voids, its interior can contain subregions of even lower density separated by faint ridges. Some of the few galaxies may lie not at the deepest center, but in slightly denser pockets, where small halos are more likely to form. This produces a graded interior, with the emptiest zones near the core and a somewhat richer, though still sparse, distribution toward intermediate radii. In studying such interiors, a persistent challenge is completeness. The faintest galaxies are hard to detect, and the gap is defined partly by what is not seen. Analysts estimate how many galaxies could be present but unseen by modeling how detection probability depends on brightness and size, and by accounting for how survey sensitivity changes across the sky and with distance. A low surface brightness galaxy can be missed even when its total light would be detectable if concentrated. Observations indicate that hidden populations of faint galaxies exist in general, and it remains uncertain in many specific reported gaps how large the unseen contribution is, especially far away where distance uncertainty and limited depth blur the map. Despite these limits, the interior is not merely a blank in a chart. It is an environment with definable properties, fewer massive halos, wider separations, reduced interaction rates, and a bias towards small galaxies whose growth is slow and uneven. These properties follow from the same gravitational growth that builds clusters and filaments, viewed from the opposite side of the density landscape. When a gap is confirmed as a true underdensity rather than a survey artifact, it becomes a calm laboratory for understanding how galaxies form and change when the usual pressures of crowded neighborhoods are muted, and when the large-scale pattern of the universe expresses itself through measured quietness and long spacing. Within the interior of a large cosmic gap, ordinary matter is present mostly as intergalactic gas, meaning gas that lies between galaxies rather than inside them. This material is extraordinarily thin, yet across tens or hundreds of millions of light-years it still represents a significant fraction of the universe's ordinary matter. The shortage that defines a gap is therefore mainly a shortage of luminous galaxies, not an absolute absence of matter. The gas is dominated by hydrogen and helium, the simplest elements formed early in cosmic history. Heavier elements exist in much smaller amounts, made later inside stars and carried outward by winds and explosions. In low-density interiors, enrichment is usually weaker than in crowded regions because there are fewer galaxies to supply metals, yet traces can still be found and can reveal the gas's state. The gas also contains free electrons and ions because most intergalactic hydrogen is ionized rather than neutral. Ionized means an atom has lost an electron. A diffuse background of ultraviolet light, produced by many stars and by active galactic nuclei, keeps hydrogen ionized across much of the cosmos. In a void-like interior, recombination is slow because particles meet rarely, so the same background light can maintain ionization with less effort than in denser environments. Temperature in this thin medium reflects a balance between gentle heating and slow cooling. Ultraviolet ionization warms the gas. Expansion cools it as space stretches. Because collisions are rare, the gas does not behave like air or water, and it does not easily radiate away heat unless conditions allow specific atomic transitions. Much of the diffuse intergalactic medium sits at temperatures of several thousand to tens of thousands of degrees Celsius, warm enough to stay ionized but too faint to shine strongly in visible light. Pressure smooths some small clumps, making the deepest interiors relatively uniform. Closer to massive structures, shocks can heat gas to millions of degrees Celsius and produce X-ray emission, but deep gap interiors are less likely to host frequent strong shocks, so the hottest phases are less common there. Since the gas is dim, the main way to study it is to look for its imprint on light from far beyond. Bright distant sources provide backlighting, and the gas removes narrow bands of wavelength, producing absorption lines, quasars, extremely luminous active galactic nuclei are especially useful because their spectra are bright and can be measured in detail along a single line of sight. Many small dips appear where intervening hydrogen absorbs light at a characteristic wavelength that has been shifted by expansion. This pattern is called the Lyman alpha forest. It traces mild fluctuations in gas density and reveals that intergalactic space is filled with structured, ionized material even where galaxies are sparse. In some directions, bright background galaxies can also serve as beacons, though their spectra are usually fainter and more difficult to use at high precision. Across a large gap, absorption lines tend to be fewer and weaker on average, consistent with lower density. Occasional stronger absorbers still appear, often associated with the few galaxies and small groups inside the region or near its rim. Absorption is sensitive to very thin material, but it samples only narrow pencil beams. A broad interior cannot be mapped completely unless many background sightlines cross it, and bright quasars are rare. For this reason, observations often provide partial slices through the region rather than a uniform three-dimensional picture, and uncertainties remain about how smooth the interior gas truly is. Direct emission from the gas is much harder to detect. In many cases, the brightness depends strongly on density, so the most rarefied regions become almost invisible. Some ultraviolet emission lines could, in principle, reveal diffuse gas, but Earth's atmosphere blocks much ultraviolet light, and space observations must contend with extremely low surface brightness. In the hottest gas, X-ray emission is possible, yet a cool, thin interior may not reach the temperatures and densities needed to glow. As a result, studies often detect emission mainly near denser boundaries, while the deepest interior yields only upper limits that still help constrain how much gas can remain hidden. Radio techniques offer a different handle on diffuse material. Neutral hydrogen has a spectral feature near a wavelength of 21 centimeters, yet gap interiors are usually too ionized for this signal to be strong. Fast radio bursts provide another type of backlight, because their signals are delayed by free electrons along the path. With enough events and reliable distances, the total electron content through underdense regions can be estimated, though uncertainty remains in separating contributions from the source environments. Intergalactic gas in a gap also reflects the history of reionization, the early era when the first galaxies flood space with ultraviolet light and ionize hydrogen on large scales. Low-density regions are expected to ionize early because radiation travels more freely through thinner material. Observations indicate a broadly ionized intergalactic medium at later times, but fine details remain uncertain, including how uniform the ultraviolet background is across very large distances and how much patchiness persists from the uneven distribution of sources. A related uncertainty concerns the accounting of ordinary matter in the nearby universe. Measurements of stars, galaxies, and hot cluster gas do not capture the full amount implied by cosmological observations. A leading view is that much of the remainder lies as warm, hot intergalactic gas in and around filaments, heated during structure growth. In the deepest interiors of gaps, that warm, hot phase may be less prominent, replaced by cooler ionized material that is difficult to weigh. Determining how much mass lies in each phase remains challenging, because the best traces are faint, limited to sparse sightlines, or sensitive mainly to denser regions. In this view, a mysterious gap is not a clean cavity. It is a region where bright galaxies are uncommon, and where the dominant ordinary matter becomes a nearly invisible medium of ionized gas. The gas reveals itself mostly through delicate absorption patterns, and through careful limits on how much emission can be present without being seen. Its state is shaped by the diffuse radiation field of the cosmos and by slow, large-scale flows that move ordinary matter from underdense interiors toward denser surroundings over immense spans of time. Within the broad interior of a cosmic gap, the dominant substance by mass remains unseen. Dark matter does not emit light, does not block light the way dust can, and is detected mainly through its gravity. In the standard cosmological picture, dark matter forms the main framework of large-scale structure, where that framework is dense. Ordinary gas collects and galaxies form in abundance. Where it is thin, fewer deep gravitational wells develop, and the visible contents of space become sparse. A reported gap, therefore, has a practical meaning. It indicates that the luminous traces of matter are unusually scarce across a large volume, and it invites a careful check of how closely that scarcity matches the true distribution of total mass. The expectation from the standard model is that a gap corresponds to an underdensity in dark matter, as well as in ordinary matter. Simulations that begin with early density variations consistent with the cosmic microwave background and evolve them forward under gravity produce voids naturally. In those simulations, an initially underdense region expands a little faster than average because it has less mass to slow its local expansion. Over long time, matter drifts away from the center and collects towards surrounding filaments and walls. The interior becomes a broad basin in the mass field, not empty, but measurably below the cosmic mean. In such a basin, the gravitational potential is shallower than average, and the net pull on material points outward toward denser surroundings. Even when the mass deficit is real, visible maps can exaggerate it. Galaxies form inside dark matter halos, and halos form most readily in the highest peaks of the mass field. In an underdense region, the number of high-mass halos drops sharply. This can remove many bright galaxies even when the total mass deficit is only moderate. A gap defined using only luminous galaxies can therefore look deeper than the underlying mass depression. When surveys reach fainter galaxies, they often reveal that the interior contains a thin population of small systems after all. This change does not erase the underdensity, but it reminds observers that light traces only a selected part of the mass landscape. To estimate the dark matter content of a gap, astronomers rely on methods that do not depend on finding many bright objects inside it. The most direct is weak gravitational lensing. Mass along a line of sight bends the paths of photons and subtly distorts the shapes of background galaxies. A mass concentration produces a characteristic stretching pattern around it. A mass deficit produces the opposite tendency, a slight reduction in the focusing effect that would otherwise be present. The signal from a single underdense region is faint. It competes with the natural variety of galaxy shapes and with the lensing influence of unrelated structures in front and behind. Analysts therefore average over large numbers of background galaxies and compare the region to surrounding control areas. When a gap is truly a broad mass underdensity, the average lensing pattern is consistent with less mass than average across the chosen volume, though the uncertainty can remain large. A second route to the mass field uses galaxy motions near the boundary. Redshift measures expansion, but it also includes the effects of local motion. Around an underdensity, galaxies tend to stream outward from the interior toward denser regions. This coherent outflow creates a distinctive distortion in redshift space. Structures can appear slightly squashed or stretched along the line of sight depending on how the velocity field projects onto the survey geometry. By modelling these distortions, astronomers infer the depth and shape of the gravitational potential that would drive the observed flow. The inference does not require many galaxies deep in the interior, because the rim usually provides most of the measurable traces. The approach does depend on the relation between galaxy distribution and mass distribution, and on how well the velocity model represents real flows, so it is treated as a constrained estimate rather than a direct measurement. A third line of evidence comes from how the gap fits within the broader pattern of clustering. If a region is underdense in mass, then on average fewer halos form there, fewer galaxies appear, and the surrounding walls and filaments become relatively more prominent. When astronomers compare the observed density profile around the gap to profiles produced in simulations, they test whether the shape resembles typical void-like basins in the standard model. This comparison is not a proof by itself, but it can show whether the region's scale and contrast are compatible with known structure growth. Inside the gap, the dark matter field is not flat. Simulations show a quieter version of the same hierarchy found elsewhere. Small halos persist, thin internal ridges remain, and the deepest underdensity tends to lie near the center. The difference is that the peaks are lower and more widely spaced. Massive halos, which host the brightest galaxies, become rare, so the visible map grows sparse even when the mass field still contains gentle structure. This is why a gap can look like a near-empty cavity in a bright galaxy survey, while still holding a subtle population of low-mass systems and a continuous, though thinned, dark matter distribution. Uncertainty remains an essential part of this layer of analysis. Weak lensing integrates mass along the entire line of sight, so the signal of a gap can be diluted or confused by other structures. Velocity-based inferences depend on assumptions about how galaxies trace the mass field and how accurately local motions are modelled. Survey systematics can also mimic broad underdensities if completeness varies across the sky or with distance. For these reasons, observations can indicate that a region is underdense in traces and consistent with a mass underdensity, while it remains uncertain exactly how deep the mass deficit is and how smooth its interior truly is. Within those limits, the interpretation stays calm and consistent. A cosmic gap is best understood as a broad depression in the dominant dark matter framework, expressed in visible surveys as a shortage of luminous systems. Dark matter shapes the region by setting where halos can grow, and by guiding slow flows of matter toward denser boundaries. The interior's quietness is therefore not the absence of structure, but the presence of structure at low amplitude, spread thinly across an immense volume. Across the lifetime of the observable universe, a large gap is shaped by slow differences in gravity that begin as slight imbalances and accumulate into a broad landscape. The process starts when the early cosmos holds small variations in density. Where density is lower than average, there is less mass to pull inward, and the region expands a little faster than its surroundings. This is not a local burst. It is a gentle divergence in motion layered on top of the overall expansion of space. Over immense spans of time, that divergence matters. It causes matter to drift away from the center of the underdensity, while surrounding regions, slightly denser, slow a little more and gather additional material. After the universe becomes transparent to light, ordinary matter and dark matter begin to grow structure together. Radiation no longer keeps ordinary matter tightly coupled to the light field, and gas can fall toward the dark matter framework. In this era, the density differences are still small, and growth is described as linear, meaning contrasts increase in proportion without sharp distortions of shape. In a linear phase, an underdense region keeps a broadly similar outline while its deficit deepens relative to the mean. As time passes and gravity has longer to work, growth becomes non-linear, meaning dense regions collapse more strongly, filaments sharpen, and void interiors become more distinct. A gap described in a modern survey is the mature product of this long transition. The timescale is set by the expansion rate and the amount of matter present. When matter density is higher, gravity has more influence and structure grows more quickly. As the universe expands, the average matter density falls and growth slows. In the standard cosmological model, expansion begins to accelerate several billion years ago, associated with dark energy. Acceleration does not erase structure, but it reduces the rate at which new structure forms. Clusters and filaments still evolve, and voids still expand. Yet the pace of change becomes gentler than it would be in a purely matter-dominated cosmos. For a gap, this means much of its deepening occurs earlier, when the universe is denser and gravity more effective. As filaments and clusters grow, they draw matter out of nearby underdense basins. The outflow from a void interior is not a single stream but a broad pattern of motion, with matter following shallow gradients towards surrounding walls. These flows are small compared with the speed of light, yet over billions of years they move material across huge distances. The interior becomes more rarefied, and the rim becomes more defined. The shape of the gap reflects both its initial conditions and the environment around it. If the early underdensity is nearly spherical and relatively isolated, its later form tends toward a round basin, with a smooth rise in density toward the boundary. If the underdensity lies between strong neighboring structures, the surrounding pull is uneven, and the region can become elongated or flattened. Nearby massive clusters create tidal forces, meaning differences in gravitational pull across the region that stretch it along one direction and compress it along another. Over time, such forces sculpt the basin into an irregular form, while preserving the basic character of a low-density interior surrounded by denser ridges. As underdense regions expand, they can merge. A thin wall separating two basins can weaken as matter drains away and as expansion carries the basins outward. When the wall becomes faint, the two regions behave as a single larger underdensity. This merging produces a hierarchy where large gaps contain smaller subvoids and faint internal ridges. A very large reported gap can therefore represent the combined interior of several underdense regions that have gradually joined, leaving a complex interior with gentle gradients rather than a uniform emptiness. The evolution of a gap is expressed through the formation of dark matter halos. Halos are the gravitational wells in which galaxies form, and their abundance depends on local density. In an underdense region, halo growth is suppressed, and the highest mass halos are strongly reduced. Halos still form, but they are typically smaller and more widely spaced. This produces a central observational signature, fewer bright galaxies and fewer massive groups inside the interior, even when the total mass deficit is not absolute. Meanwhile, the boundary becomes a preferred location for growth, because material leaving the interior contributes to the build-up of filaments and walls. Ordinary matter follows this framework but adds its own smoothing. Gas pressure resists compression in the thinnest regions, and the diffuse radiation field keeps much of the intergalactic gas ionized and warm. In dense environments, gas shocks and cools, building stars efficiently. In deep interiors, gas is more diffuse, cooling is less effective, and star formation sites are rarer. This difference affects how the gap appears in light, because the visible depth depends on the efficiency of galaxy formation, as well as on total mass. A gap can therefore look especially empty in bright galaxy maps, while deeper observations reveal a sparse population of small systems tracing faint internal structure. The motion around a gap is not only a feature of simulations. Coherent outflows influence redshift space maps, altering apparent shapes along the line of sight. the same flows, when modelled, help estimate the depth of the gravitational basin. Observations indicate that void-like outflow patterns are present in the large-scale distribution, consistent with the standard model. For many individual reported gaps, it remains uncertain how much of the apparent size and depth is affected by distance errors, sparse sampling, or the method used to define the boundary. Within those limits, the story remains one of gradual, cumulative change. A gap does not appear suddenly. It develops as an underdense region expands slightly faster than average, drains matter toward its rim, and merges with neighbouring basins. Its contrast reflects the era when gravity is most effective at building structure, and is later moderated by the slowing of growth in an accelerating universe. The result is a present-day underdensity that carries the memory of early fluctuations and long gravitational evolution, expressed in the spacing of galaxies and the quiet architecture of the cosmic web. Light that comes from far beyond a cosmic gap carries subtle marks of the mass it passes on the way. Even when the interior holds few bright galaxies, it still lies within a gravitational landscape that bends paths and shifts energies. These effects are small, and they rarely stand out in a single measurement. They emerge through careful averaging, through comparisons between maps, and through the steady separation of weak signals from larger noise. The most uniform background is the cosmic microwave background, the ancient afterglow released when the early universe becomes transparent. It arrives from all directions with nearly the same temperature, and it carries faint patterns that reflect early density variations. A large gap exists long after that background light is emitted. Background photons cross the later universe and experience weak changes as they move through evolving gravitational potentials, the broad wells and hills made mostly by dark matter. A gravitational potential describes how gravity shapes motion and energy in a region. In a dense structure, the potential is deeper, and in an underdensity it is shallower. When a photon falls into a potential well, it gains energy, and when it climbs out, it loses energy. If the potential is stable while the photon crosses it, the energy gained and lost cancel almost exactly. If the potential changes during the crossing, the cancellation is imperfect, leaving a small net shift in the photon's energy and therefore in its observed temperature. This process is called the integrated Sachs-Wolf effect. It is most important when the growth of structure slows and gravitational potentials begin to change with time, as happens when the expansion of the universe accelerates. A related, even smaller contribution comes from nonlinear evolution, sometimes called the Rees-Siemmer effect, where changing structures shift photon energies beyond the linear expectation. For typical voids and filaments, this contribution is minor, but it is included in detailed modelling of large features. In an accelerating universe, large-scale potentials tend to decay slightly in amplitude. A dense region's potential becomes a little less deep over time, and an underdense region's potential hill becomes a little less high in the same sense, because contrast growth slows. When a background photon crosses a decaying potential well, it gains a little more energy overall, producing a slightly warmer patch. When it crosses a decaying potential hill associated with an underdensity, it loses a little more energy overall, producing a slightly cooler patch. The expected temperature shift from a single void-sized underdensity is small, often far below the variations already present in the cosmic microwave background. For this reason, the effect is commonly studied statistically by cross-correlating maps of large-scale structure with maps of the background, looking for a tendency for underdense regions to align with slightly cooler background patches and dense regions to align with slightly warmer ones. A large reported gap can be examined by asking whether the cosmic microwave background in that direction shows any unusual temperature feature. Some studies explore apparent alignments between very large underdensities and unusually cool background regions. Observations can indicate a qualitative match in a particular case, yet it remains uncertain whether the match is meaningful because the background contains its own chance patterns. The background's larger-scale temperature features are limited by cosmic variance, meaning that the universe provides only one realization of those random early fluctuations. So statistical certainty is hard to reach for individual alignments. A gap can be genuine and still have a background imprint too weak to separate from chance variation. Beyond temperature, the background also carries lensing signatures. Mass along the line of sight deflects photons, remapping the background pattern slightly. Dense structures focus and shear the background, and underdensities produce the opposite, a small reduction in convergence compared with the mean. This lensing is measured through coherent distortions in the statistical texture of the background across the sky. Analyses reconstruct a lensing convergence map from these distortions, and this map can be compared with galaxy surveys. A broad gap, if it corresponds to a true mass underdensity, can be associated with a small dip in the reconstructed convergence. The signal is weak and depends on resolution and noise in the reconstruction, and it can be diluted by unrelated mass in front and behind. Other background sources can also be used as screens. The distribution of distant galaxies behind the gap can show small magnification effects. In dense regions, weak lensing can increase the apparent brightness of background galaxies and can change their observed number counts. In an underdensity, the opposite tendency can occur, with slight demagnification. The effect is small and competes with intrinsic variations in galaxy populations, yet it can be measured by averaging over large samples and correlating counts with foreground structure maps. Time-variable background sources add another perspective. Fast radio bursts and other transient signals can show delays related to the total number of free electrons along the line of sight. A deep underdensity could reduce the average dispersion contribution from intergalactic space in that direction. In practice, the measurement depends on knowing the distance to the burst and on separating contributions from the burst environment, its host galaxy, and the Milky Way. Current observations indicate that dispersion measures trace the overall distribution of ordinary matter in a broad way. But for any single large gap, it remains uncertain whether enough events exist in the right direction to isolate a clear deficit. All these methods share the same challenge. A gap is a low-density region, so most signals associated with it are small differences from a mean value rather than strong features. The background radiation and background sources are influenced by everything along the line of sight, so a nearby cluster or a distant filament can partially mask or mimic the expected effect from the underdensity. Analysts respond by modeling the full matter distribution, by using control regions, and by asking whether multiple independent probes point in the same direction. When they do, confidence grows that the gap is not only a shortage of visible galaxies, but also a real depression in the gravitational landscape. When they do not, the result can still be consistent with a genuine gap whose imprint falls below present detection limits. Light-based probes of a large cosmic gap depend not only on what the universe contains, but on how faint signatures are extracted from noisy skies. The imprint of an underdensity is small compared with the natural variations in the backgrounds used to detect it. Background galaxies have their own shapes and clustering. The cosmic microwave background has its own temperature pattern set long before the gap forms. Quasar spectra vary from source to source. Instruments add noise and the Milky Way adds foreground structure. The analysis therefore relies on careful averaging and on separating weak, coherent signals from stronger, unrelated ones. The first step is to define the gap in a way that can be applied consistently. A center is chosen along with an effective size and a boundary definition tied to the survey that identifies the underdensity. Because the boundary is gradual, analysts often summarize the region by a radial profile, meaning how tracer density changes with distance from the chosen center when averaged over directions. This profile is a practical description, not a claim of perfect roundness, and it is tested for stability under reasonable changes in the void-finding method. With a defined region, a background dataset is prepared. For weak gravitational lensing of galaxies, the relevant information is the measured ellipticity, the apparent shape of each background galaxy after accounting for the instrument's blurring and for observational biases. The lensing signal is a tiny, coherent alignment pattern that appears only after many galaxies are combined. For cosmic microwave background lensing, the relevant information is subtle remapping of the background's texture, reconstructed into a convergence field that estimates projected mass. For integrated Sachs-Wolf studies, the relevant information is temperature variation on large angular scales compared against the distribution of foreground structure. These backgrounds are filtered and cleaned. Galaxy lensing analyses correct for point spread function effects that can mimic shear. Cosmic microwave background maps are cleaned of foreground emission from dust and synchrotron radiation, using multi-frequency information and component separation. Spectral absorption studies normalize quasar continua so that weak absorption lines can be measured consistently. Each correction adds uncertainty, so analysts apply the same pipeline to simulated data with known inputs and test whether the corrections remove known systematic patterns without erasing real signals. Averaging is central. Many studies stack multiple underdense regions, aligning them by their centers and combining measurements to enhance a weak signal. For a single reported large gap, analysts still use averaging in a different way, combining large numbers of background galaxies or many pixels of a background map within a defined aperture. They may use compensated filters, which subtract the mean signal in a surrounding annulus from the signal in the interior, reducing sensitivity to slow drifts across the sky. They may also weight the data according to an expected signal shape to improve sensitivity when the observed region resembles typical profiles from simulations. Template choice is guided by simulations. In the standard cosmological model, typical void density profiles and the corresponding lensing and temperature signatures can be predicted statistically. Mock skies are generated that include survey geometry, distance errors, and noise. Then the same void finding and signal extraction steps are applied. The distribution of recovered signals from these mocks becomes the reference for interpreting the measurement and for understanding how much the result depends on analysis choices. Uncertainty estimation is treated with the same care as the signal itself. Measurements within and around the gap are correlated because nearby sky patches share the same large-scale background patterns, and because survey depth varies smoothly. Analysts estimate covariance using simulations by dividing the survey area into many subregions and repeating the measurement with each subregion omitted, or by resampling background sources in a way that preserves their clustering. Masks are handled gently rather than ignored. Edges of survey footprints are often apodized, meaning softened, so that sharp boundaries do not introduce artificial patterns in filtered maps. These steps determine whether an apparent feature is a stable detection or a fluctuation that shifts when the analysis window moves slightly. Control measurements provide safeguards. Analysts repeat the same measurement around random points or around regions chosen to match the survey footprint but not the structure, and they expect the average signal to vanish. In galaxy lensing, Additional checks separate true shear patterns from patterns that can arise from residual systematics in shape measurement. In cosmic microwave background analysis, cross-checks against foreground maps constrain how much residual dust could leak into the result, and reconstructions built from different frequency combinations are compared for consistency. These tests do not remove uncertainty, but they bound the size of spurious signals. Absorption studies face a different limitation. They sample thin lines through space, so they depend on how many bright background sources happen to lie behind the gap. When enough suitable sightlines exist, absorption strength through the region can be compared to nearby control sightlines. When only a few exist, the result remains uncertain because a single strong absorber unrelated to the gap can dominate the measurement, and because distance uncertainty can place absorbers inside or outside the region by modest shifts in redshift. Even with clean extraction, interpretation requires a connection between the measured quantity and the underlying matter or gas. Lensing measures projected mass integrated along the line of sight, so unrelated structures can dilute the deficit. Integrated Sachs-Wolf measurements depend on how gravitational potentials change with time, which depends on the expansion history and on structure growth. Absorption depends on gas density, ionization, and temperature, influenced by the ultraviolet background and by local sources. For this reason, analysts compare observed signals to forward models from simulations and treat conclusions about depth and mass deficit as constrained rather than absolute. In this layer of work, the gap becomes a test of method as much as a feature on a map. When different probes point toward a consistent underdensity, confidence grows that the region corresponds to a real depression in the matter field. When probes disagree, the outcome can reflect limits of depth, resolution, and contamination rather than an absence of the underdensity itself. A reported gap becomes most delicate to interpret when the discussion turns from mapping to meaning. The map can show a broad underdensity in the distribution of galaxies, and follow-up probes can suggest a corresponding dip in mass or gas. Yet a further step remains, deciding how unusual the feature is within the standard picture of structure growth. This step is statistical, because the universe contains randomness in its initial conditions, and because observers see only one cosmic realization. The issue is not whether voids exist. The issue is whether a particular gap is so large or so deep that it strains expectations, or whether it sits within the broad tail of normal variation. The standard cosmological model begins with early density differences that are treated as a random field with measured properties. Random here does not mean without rules. It means that the exact placement of peaks and basins is not fixed in advance, even though their overall distribution and typical amplitudes follow a pattern constrained by observations of the cosmic microwave background and by galaxy clustering. When gravity evolves this field forward in time, some regions become clusters and filaments, and some become voids. A survey that samples a large volume therefore contains many underdense regions, and a few appear extreme simply because the survey searches so widely. Astronomers describe this with the idea of statistical significance, meaning how strongly an observed feature stands out compared with what would be expected under a chosen model, given the survey's noise and limitations. A strong significance suggests the feature is unlikely to appear by chance within the model. A weak significance suggests the feature is compatible with ordinary variation. In practice, the result depends on how many opportunities the survey has to produce an extreme feature, and on how the feature is defined. The number of opportunities is often the quiet driver. A survey volume can be divided into many overlapping regions where a void-like underdensity could be measured. Even if the probability of finding a very large basin in any one region is small, the probability of finding at least one such basin somewhere in the full volume can be much larger. This is a trial factor, where searching widely increases the expectation for an extreme outcome. When a gap is highlighted after a broad search, careful analysis asks how often a similar or larger feature appears anywhere in mock surveys of the same size, not just at a chosen location. Definition choice also matters. A gap can be described by its effective radius, its depth relative to the mean, its shape, or its profile across distance. Small changes in smoothing scale or boundary criteria can shift these values. To reduce dependence on a single choice, analysts test a range of reasonable definitions and ask whether the gap remains notably large or deep under these alternatives. When the gap appears extreme only under one narrow definition, the claim weakens. When it remains extreme under many reasonable definitions, the claim strengthens. The most fundamental limitation is cosmic variance, meaning uncertainty that arises because the observable universe provides only one sample of the underlying random process. The limitation is strongest for very large scales, because there are fewer independent regions of that size within the observed volume. A single unusually large gap can therefore be hard to classify with high confidence, because the baseline expectation for the rare tail is itself uncertain when only a limited number of comparable regions exist. Sampling noise adds another layer. Galaxies are discrete objects, and a catalogue provides only a finite number of traces in a sparse region. The count in a given volume can fluctuate simply because of limited sampling. This shot noise can make an underdensity appear deeper or shallower than it truly is in the underlying mass field. Surveys reduce this by using larger samples and by smoothing over scales large enough to average out small number fluctuations. But no survey eliminates the effect entirely. Distance uncertainty adds to this noise by scattering galaxies across boundaries and softening contrasts. Systematic errors behave differently from random noise. They can create patterns that mimic a gap, or they can hide part of a true gap. A slowly varying completeness gradient across the sky can produce an apparent underdensity aligned with survey depth rather than cosmic structure. Residual dust extinction can reduce galaxy counts in specific regions. Because these effects are not random, they are tested through cross-checks with independent data and through control measurements around random locations. When systematics remain possible at the same scale as the claimed gap, the statistical assessment must include this uncertainty, widening the range of plausible depths and reducing the claimed rarity. Comparisons with simulations help anchor expectations. Large simulations generate many voids and provide statistics for the distribution of extremes under a chosen cosmology. Yet simulations still require assumptions about cosmological parameters and about how galaxies trace dark matter halos. Analysts therefore build mock catalogues that match the survey footprint and selection, then apply the same void-finding method to the mocks. If the reported gap resembles the most extreme examples in the mocks, it can be rare but still compatible with the standard model. If it lies beyond the mock distribution, the result can point to unmodelled survey effects, to limitations of the galaxy tracing model, or to tension with the assumed cosmology. Statistical interpretation also depends on what is being claimed. A claim that a gap contradicts the standard model requires showing that it lies far outside predicted distributions, after accounting for trial factors, noise, and cosmic variance. A more restrained claim states that the feature lies near the far tail, unusual but not inconsistent. In careful work, rarity is described without treating rarity alone as evidence for new physics. Within this framework, uncertainty is stated plainly. Observations indicate the presence of large underdense regions, and models indicate that broad surveys should contain some unusually large examples. It remains uncertain for any single reported gap, whether its apparent size and depth represent an extreme of the underlying mass field or an extreme in the chosen traces combined with survey limitations. It also remains uncertain how tightly the probability of such an extreme can be stated, because the larger scale statistics carry intrinsic limits from cosmic variance. The gap is therefore interpreted as a measurable feature with a range of plausible strengths, placed within a distribution that is broad, noisy, and shaped by the fact that only one universe is available to observe. To judge whether a reported gap fits the standard picture, astronomers compare it with synthetic universes built on computers. A simulation starts from an early time when matter is almost smooth. The starting field is a three-dimensional pattern of tiny differences in density and motion, whose statistics match what is inferred from the cosmic microwave background. A random seed selects one particular realization. Then gravity and cosmic expansion evolve that realization forward through time. Over billions of years of simulated evolution, clusters, filaments, walls, and wide underdense basins emerge without being placed by hand. Many large simulations follow only dark matter. Dark matter is represented by an enormous number of particles, each one standing in for a large clump of mass. The particles attract one another through gravity, and their motions are updated in small time steps while the scale of the universe grows. When the volume is large enough, these gravity-only simulations contain very rare structures simply because they include so many independent regions. A gap in such a volume is defined as a basin in the mass density field, and its size, shape, and depth are measured with void-finding algorithms similar to those used on survey catalogues. Observations detect galaxies rather than dark matter, so simulations must connect light to mass. One route includes ordinary matter and follows gas alongside gravity. Gas can shock and heat, cool by radiation, and form stars. Energy from stars and from active galactic nuclei can move gas and change where later star formation occurs. These processes happen on scales far smaller than the simulated volume, so they are represented with approximate rules. Even with those approximations, such simulations help test how strongly an underdense region in mass becomes an underdense region in visible galaxies. A second route keeps the large dark matter-only volume and adds galaxies afterward. The simulation identifies dark matter halos, gravitationally bound clumps found by searching for overdensities and testing whether their particles remain bound. Galaxies are then assigned to halos using statistical prescriptions tuned to reproduce observed galaxy number counts and clustering. Some prescriptions place one main galaxy in each halo above a mass threshold and add satellites in higher mass halos. Others match the ranked list of halo masses to the ranked list of galaxy brightnesses, creating a simple link between light and halo mass. These methods cannot capture every detail of galaxy physics, but they are effective for creating mock catalogues across volumes large enough to contain rare gaps. The comparison becomes meaningful only when the simulation is observed through the same filter as the real sky. Real surveys have incomplete footprints, masked areas, depth variations, and distance uncertainty. A mock survey therefore selects simulated objects using a selection function that reproduces these features. The mock may be built as a light cone, combining outputs from different simulation times so that nearby objects come from later epochs and distant objects come from earlier epochs. Redshift space distortions are added by including local motions along the line of sight, so the mock reproduces the same stretching and compression seen in redshift maps. Distance errors can be included by scattering the inferred positions according to an error model tied to the survey. With these steps, the same void-finding pipeline is applied to the mock catalogue. This consistency matters because void boundaries are gradual, and different definitions can yield different measured sizes and depths for the same underlying basin. The result of the mock analysis is a distribution of gap-like features that includes both cosmic variation and survey limitations. A reported gap is then compared to that distribution rather than to an idealized, perfectly sampled universe. Simulations also provide expected profiles. In the standard model, a typical underdense basin shows its lowest density near the center, and a rise toward a boundary where matter becomes more concentrated. When galaxies are used as tracers, the profile can look deeper because bright galaxies are disproportionately absent in low-density regions. Mock catalogues calibrate this by comparing the tracer profile to the true mass profile in the same simulated region. The simulated mass field can also be projected to predict weak lensing signals, then processed with realistic noise and masks to estimate what an underdensity of a given scale should imprint on background galaxy shapes. Analysts often repeat the exercise with different tracer selections, such as different brightness cuts or galaxy types, to check that the inferred basin is not an artifact of one particular population. They also test that the recovered gap statistics remain stable when the same pipeline is applied to independent simulations generated with different random seeds. The usefulness of these comparisons depends on volume and resolution. Very large volumes are needed to sample the rare tail of structure where the most extreme gaps live. High resolution is needed to represent small halos and the faint galaxies that can populate void interiors. Studies therefore combine different runs, large volume gravity-only simulations to capture rare extremes, and smaller, higher resolution runs to test how tracer populations behave inside underdense regions and at their rims. Convergence checks compare results across different resolutions to ensure that the measured void properties do not change substantially when particle mass and spatial resolution improve. Predictions also depend on cosmological parameters. The abundance of large underdensities is sensitive to the initial amplitude of density variations and to the rate at which structure grows. Simulations typically adopt parameter sets consistent with major cosmological measurements, then explore small variations to see how strongly the expected gap distribution shifts. These tests mainly widen the predicted range rather than producing a single expectation. Through this simulation work, a reported gap is translated from an emptiness in a map into a quantified feature placed within a predicted distribution that already accounts for how the survey sees the sky. When the gap's measured size, depth, and boundary profile fall within the range produced by realistic mocks, the feature is interpreted as a rare but natural basin in the cosmic web. When it remains outside those ranges after the observational filter is reproduced as faithfully as possible, the most immediate conclusion is that either the survey systematics or the tracer modelling is incomplete, and that improved data and improved synthetic surveys are needed before any deeper claim about the structure of the universe can be made. At the most inward point of the investigation, the gap becomes a set of statements bounded by measurement, method, and the limits of what the sky can reveal. The stronger statements are those that remain steady when tracer choice, distance reconstruction, and survey corrections are varied within reasonable bounds. In that sense, a large gap is most securely understood as an underdense region within the cosmic web, identified through a sustained shortage of galaxies across a mapped volume. Wide surveys show that matter is not spread evenly, and that broad underdense basins occupy a substantial fraction of cosmic volume. In this established context, a reported gap is not a new kind of object. but a particular example whose scale and contrast draw attention. Observations indicate that many claimed gaps persist when the simplest observational effects are addressed, when survey completeness is modelled, when the dimming from Milky Way dust is corrected, and when masked regions are treated consistently. The underdensity can remain visible as a coherent basin in the tracer distribution. The surrounding rim is often traced by filaments and walls, structures that are evident through their concentrations of galaxies rather than through absence. Where the rim is well measured and where the feature remains present in overlapping surveys, confidence increases that the gap reflects the cosmos rather than the observing pattern. From there, the most careful step is the link from tracer deficit to total mass. The standard cosmological model predicts that underdense regions in galaxies correspond to underdense regions in the dark matter field, though not in a one-to-one way. Simulations produce voids as broad depressions in mass density, with slow outflows that move matter from the interior toward denser surroundings. Measurements of void populations, including clustering statistics and weak lensing in stacked samples, are consistent with this general picture. For an individual large gap, the evidence is often compatible with a mass underdensity, yet precision is limited. Weak lensing is subtle for deficits, and it integrates mass along the full line of sight, so unrelated structures can dilute the signal. Velocity-based inferences depend on modelling redshift space distortions and on how galaxies trace mass near the rim. A cautious conclusion is that a persistent gap in tracers is consistent with a real mass depression, while the exact depth of that depression often remains uncertain within a broad range. Ordinary matter within the gap is constrained more by indirect signatures than by direct glow. Intergalactic gas is thin and mostly ionized, so it rarely emits strongly invisible light, especially in the deepest interiors. Absorption lines in spectra of distant bright sources indicate that diffuse gas fills intergalactic space, and lower density regions tend to show weaker absorption on average. The sampling is sparse because suitable background sources are rare, and the interior is difficult to map evenly. The secure statement is that the gap interior is not empty, and that ionized gas and dark matter remain present, while the detailed partition of gas phases and the precise mass accounting remain limited by sensitivity and by the scarcity of sightlines. The sense of mystery commonly arises when scale suggests extreme rarity. Here the inward work is the accounting of rarity itself. A modern survey explores an immense volume and effectively tests many possible regions for extremes. The probability of finding at least one unusually large basin somewhere in that volume can be much higher than the probability of finding one at a preselected location. And this difference matters when a feature is highlighted after a map is inspected. Mock catalogues built from simulations, filtered through realistic survey selection, provide the most practical reference. In many cases, these mocks show that very large underdensities occur rarely but naturally, especially when the most extreme example in a large volume is selected. In other cases, an observed gap lies near the edge of what the mocks produce, but that edge depends on how faithfully the mock reproduces selection effects and on how galaxies are assigned to halos. The predicted tail is therefore not a single crisp boundary, but a zone that shifts as modelling improves. Distance uncertainty is another inward limit. Redshift-based mapping is powerful, but local motions and measurement errors smear structures along the line of sight, and photometric distance estimates broaden that smearing further. A deep basin can appear shallower, and a modest basin can appear deeper, depending on how galaxies are scattered in distance and how completeness corrections are applied. Analysts mitigate this through spectroscopic subsets, cross-checks between catalogues, and forward modelling in mocks, yet residual ambiguity can remain for the most distant or sparsely sampled regions. A closely related limit lies in the relationship between light and mass. Galaxies are biased tracers, meaning they prefer denser environments and become scarce in the deepest basins. This implies that a gap measured by bright galaxies can overstate the emptiness of the mass field. Deeper observations that reach fainter systems can reduce the apparent depth in light while leaving the mass under density intact. The most secure interpretation therefore treats tracer depth and mass depth as related but distinct, with the conversion constrained by simulations and by empirical measurements of galaxy clustering. When background light is used, such as reconstructed lensing maps or large-scale temperature patterns in the cosmic microwave background, expected effects from a single underdensity are subtle. Chance alignments and line-of-sight mixing remain difficult to exclude completely for any one region. These probes are therefore most stable as checks of broad consistency, rather than as precise gauges of the depth of a single gap. Taken together, the inward core of the topic is defined by what remains after these limits are acknowledged. A large gap is a physically meaningful region within the cosmic web where tracer density is low and where the underlying mass field is expected to be below average. It is shaped by gravitational growth over cosmic time and expressed in modern maps as a broad basin surrounded by denser rims. Observations indicate that some gaps are large enough to motivate careful scrutiny of survey systematics, tracer bias, and statistical selection. It remains uncertain for many individual cases exactly how rare the feature is in the mass field and how sharply it should be bounded. Within those bounds, the gap is best held as a measured underdensity with a constrained range of interpretations, rather than as missing space, or as a demand for new physics. The story settles into a quieter scale, where the gap is no longer an impression of absence but a measured region shaped by slow physics. The observable universe holds a vast range of densities, from crowded clusters to wide basins where galaxies are sparse. In that range, a reported gap is a large underdense volume traced by fewer points of light, bounded by walls and filaments that mark where matter gathers. Its existence fits within the known pattern of the cosmic web, and its apparent size reflects both the true distribution of mass and the way surveys translate faint light into distance and density. The interior is not empty. Dark matter remains, spread thinly, forming a gentle framework of small halos and faint ridges. Ordinary matter remains as diffuse ionized gas, warmed by the background radiation field and hard to see except through delicate absorption signatures. The boundary carries clearer evidence, with more galaxies, more coherent structure, and the slow outflow pattern that moves material from underdense centers toward denser rims over billions of years. Uncertainty remains where signals are weakest. Galaxy maps can be influenced by survey depth, dust corrections, and distance errors. Lensing and background light probes can be diluted by unrelated structures along the line of sight. The rarity of an extreme gap depends on how it is defined and on how many opportunities a large survey has to find an outlier. Simulations filtered through realistic survey conditions provide the best way to place such a feature within expectations, yet modelling of how galaxies trace mass still limits precision in translating a deficit of light into a deficit of total matter. Within these boundaries, the calm conclusion holds. Observations indicate a sustained shortage of galaxies across a large region, consistent with a broad underdensity in the underlying mass field. It remains uncertain exactly how deep the mass deficit is for any single case and how far into the statistical tail it lies, but it does not require missing space. It requires only the familiar ingredients of modern cosmology: acting patiently an expanding universe, small early differences, and gravity shaping them into a landscape where emptiness and structure grow side by side, and where some basins are wide enough to be noticed as a gap.